All right, so here's an example. We know that for turbulent flow in a pipe, we need a friction factor, and we've been using friction factors to solve those problems. But how in the world are those measured for pipes such as this one? So here's a pipe. It's 12 meters in diameter, huge pipe, 2,000 meters long. This is the pipe that we're thinking of building in some kind of large, air conduit structure, perhaps to feed air to a tunnel. So how would we get the friction factor for a pipe like this? Obviously, it's not practical to build such a pipe and then see if it's going to work. So we want to first figure out how to test it. So can we test in a smaller pipe? We could do it some kind of reasonable laboratory scale to find that dpdx that we could apply to this larger pipe. So we know that in order to make that happen, we need to have geometric similarity. So we're going to go after geometric similarity first. And what we said for geometric similarity is that it has to have the same type of sizes in proportion to each other. So for instance, what that means is L1, I'm going to call this L1 and D1, that's our actual system, and this will be U1. So L1 over D1 has to equal L2 over D2. So that would be perfect geometric similarity for this particular system. Another geometric variable that's important for this system is the surface roughness. So epsilon 1 over D1 has to equal epsilon 2 over D2. We're going to see that that can be somewhat problematic, obviously. In order to get dynamic similarity, we also have to have the both ducts be circular ducts. So I think that's obvious, but the both ducts must be circular. So for this system, not a very complicated geometric system, geometric similarity is just this. We need these length to diameter ratios to be equal to each other. We need the dimensionless roughness to be equal to each other, and both ducts must be circular in their cross section. All right, for what's called dynamic similarity, this is the similarity of fluid motion. For that is what we match the Reynolds numbers. So the Reynolds number based on diameter 1 has to equal the Reynolds number based on diameter 2. Of course, that assumes that our characteristic length for our dimensionless system is going to be the diameter, which is typical of problems such as this, not the length. So we're going to go with diameter as our characteristic length, and we're going to see what system we could build that we might be able to test in a lab. So the first question is, well, this pipe is 2,000 meters long. That's well over a mile, so that's not going to fit in my lab. What's, essentially the longest pipe that I could imagine using in my lab? Well, obviously that depends on my lab situation. But I'm going to pick a simple one. I'm going to say, let's say if we think we could have a 10-meter pipe. And that's still a very long pipe, but we think we can fit that in my lab. So given that, we know that L2, we said D2 over L2 has to equal D1 over L1. I know all these values. So that gives me D2 is equal to 12 meters, the diameter of 1, over 2,000 meters, the length of 1. And that's going to be times my new length, which I'm hoping to have is be only 10 meters. So that's going to give me 6 times 10 to the minus 2 meters, which is equal to 6 centimeters. So far, so good. I can have a 6 centimeter diameter pipe. That's reasonable. That's something you can see and hold and use. And it's going to be a length of 10 meters. So I can do that. I said in my lab I can fit 10 meters. All right, so that seems okay. Now I need to figure out epsilon 1 over D1 is equal to epsilon 2 over D2. Now it's obvious that this could be difficult because we don't really control surface roughness that well. But in some cases, you can match it, truly match it, just try to find a surface that has that property. In this case, because the pipe is so big, we're going to take advantage of the fact that it's going to be essentially a smooth pipe. So if you assume that the surface roughness is 0.01 millimeters, which is not particularly small, but then you put that over this large diameter, we find that that comes out to be 8.33 times 10 to the minus 7. Well, that's extremely low. And if you look on the Moody diagram, you'll see basically that's lower than any entry for epsilon over d, which means this is a smooth pipe. So 8.33 times 10 to the minus 7 is quite a bit less than the lowest curve on the Moody diagram, where we look for, friction factors. So we can say that this is a smooth pipe. Therefore, pipe 1 is smooth. And as you recall from the Moody diagram, that's just a line along the bottom for all smooth pipes, in which this would be one of them. So if we can make pipe 2 also be smooth, then we should be okay. There are surfaces that are truly smooth. Glass is one of them. So as at the very worst, we could build a glass pipe and it would have an epsilon 2 basically of 0. So it would also be a smooth pipe. We could also just try to find some other extremely smooth surface that would allow us to get an epsilon 2 over d2 of something extremely small. So far, we are able to match the L over D ratio, the D over L ratios, and we're able to match the epsilon over D ratios by going with a smooth pipe. So the only thing now we have to do is make sure we have dynamic similarity. And so to do that, we have to calculate the Reynolds number. So we're going to calculate the Reynolds number based on, for the first pipe, because that's of course the one that we're trying to simulate. So we put in our pipe diameter, our velocity, and it had air in it. So we put the kinematic viscosity of air, and that comes out to be a big number. Not a surprise given what a giant pipe it is. 2.8 times 10 to the 6th is our Reynolds number for that first pipe. So first of all, definitely turbulent. So that's one reason we're doing this experiment. So we knew that was probably going to be the case. So it's solidly turbulent. And the reason that matters is because if it weren't turbulent, we wouldn't need to do this experiment. Laminar flow is well known, and we could just model it and get the friction, that we can figure out what the pressure resistance was, or frictional effects. But because it's turbulent, we know we have to do an experiment to find that friction factor. So we have to run some kind of experiment. The other thing we want to know is whether we really have to deal with the entrance length. The entrance length, of course, is about 10 diameters for turbulent flow, which in this case, pipe 1 is equal to 120 meters. Well, that's a long distance, but it's a lot less than 2,000 meters. So we're in good shape. It is fully developed for most of the flow, so we can treat it as a fully developed flow, and therefore we can go after a friction factor for this. So we have to match the Reynolds number for this Reynolds number for pipe 2. So in the next lecture, we'll look at how we would get that matching Reynolds number.